right now, if you could somehow step outside this solar system and look back at the sun, the star that has warmed every living thing that has ever existed on this planet, the star that ancient civilizations worshipped as a god, the star whose light takes 8 minutes to reach your face, even traveling. At 670 million miles per hour, it would appear as nothing more than a faint point of light, a single pixel against the black, a candle viewed from the far end of a very long corridor. That star, our star, measures 865,000 miles across. You could line up 109 Earths side by side across its diameter and still not reach the other edge. You could pour 1.3 million copies of this planet into its interior and not fill it. By every measure available to human experience, the Sun is incomprehensibly large. It contains 99.86% of all the mass in this solar system. Every planet, every moon, every asteroid, every comet, every dust grain orbiting within 50 billion miles, all of it together does not even approach 0.2% of what the Sun weighs. And yet, there exists right now a star so vastly larger than our Sun that if you replaced our Sun with it, if you placed its core where our Sun currently burns its surface, would not stop at Mercury, it would not stop at Venus, it would not stop at Earth or Mars or the asteroid belt or Jupiter. Its surface would extend past the orbit of Saturn, the planet with the rings, the planet that takes 29 years to complete a single orbit around what we call the Sun. That is where the surface of this star would sit, not its corona, not some diffuse outer atmosphere. Its visible surface, the boundary where light finally escapes into space. Everything inside that boundary, every planet, every moon, every rock, every robot we have ever sent into the sky, every fragment of every world that has ever existed in the inner solar system would be gone, dissolved, swallowed whole by a single star. Its name is Stevenson 2 to 18. You have probably never heard of it. Most people have not. It sits 2,000,000 light years from Earth, buried behind some of the thickest curtains of interstellar dust in the galaxy, invisible to every optical telescope ever built. No human eye, aided or unaided, has ever seen its light in the way we normally think of seeing. It does not appear in classical star charts. It was not named by ancient astronomers who traced patterns in the night sky. It was not discovered by Galileo or Herschel or Hubble. It waited hidden for the specific technology that could finally see through the dust, and that technology did not exist until recently. When astronomers finally measured it, the number they found was this: approximately 2150 times the radius of our Sun, a volume roughly 10 billion times larger, a surface area 4 million times greater, a luminosity equivalent to 440,000 suns burning simultaneously. If you enjoy journeys that shatter every intuition you have ever built about how large things in the universe can actually be, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach more people, and what we are about to examine together deserves to be understood as widely as possible, because this is not a theoretical object. This is not a simulation or a prediction or a mathematical extrapolation. This is a real star, confirmed by real measurements, burning right now, in a real corner of the Milky Way. We have found it, we have measured it, and what the measurements reveal will permanently alter how you see every star in the night sky. Get yourself comfortable. Let's begin. The year was 1990. An American astronomer named Charles Bruce Stevenson was doing something that sounds almost mundane by the standards of modern space science. He was making a list. Stevenson worked systematically through infrared observations of the sky, cataloging bright sources of infrared radiation, the kind of light invisible to human eyes, but detectable by the increasingly sophisticated sensors coming online. For that era, he was not hunting for records. He was not searching for the largest star in the universe. He was doing the foundational, unglamorous work of science, documenting what is there so that future researchers would have somewhere to start. His catalogue entry for a particular cluster of stars in the constellation Scutum, a small faint constellation in the summer sky that gazes toward the inner spiral arms of the Milky Way, was just another data point among thousands. He noted a dense grouping of infrared sources, He assigned it a number, Stevenson 2. He moved on. He had no way of knowing what was inside it. Scutum sits in a direction that looks toward the heart of our galaxy. When you face that part of the sky on a dark summer night, you are looking toward the densest, most crowded regions of the Milky Way regions, packed with stars, with gas clouds, with spiral arms folding over one another in layers stretching back tens of thousands of light years. It is one of the richest patches of sky for infrared astronomy. It is also one of the most obscured. The same density that fills it with stars fills it with the dust. Those stars produce silicate grains, carbon particles, complex molecules that form in the cold spaces between suns and drift outward for millions of years, accumulating into vast clouds that block visible light the way a thick fog bank blocks a lighthouse. The extinction along the line of sight to Stevenson 2 measures approximately 20 magnitudes in visible light. That number requires translation. A difference of 1 magnitude in astronomy corresponds roughly to a factor of 2.5 inches brightness. A difference of 5 magnitudes equals a factor of 100. 20 magnitudes means that in visible wavelengths, an object appears approximately 100 million times fainter than it would without the dust in the way. 100 million times fainter. Imagine a candle burning in a room at the end of a long corridor. Now imagine placing a wall of fog between you and that candle fog, not 10 feet thick, not 100 feet thick, but fog dense enough to dim the flame by a factor of 100 million. You would see nothing. Not a glow, not a hint, nothing. The candle is still burning, the light is still leaving it, but it never reaches you. That is why Stevenson 2-18 was invisible to astronomy for centuries. Not because it is faint, it radiates with the power of nearly 500,000 suns combined, but because between us and it the universe has placed a curtain of cosmic dust so thick that visible light simply cannot penetrate it. Optical telescopes, no matter how large, no matter how precisely engineered, see only darkness in that direction. The solution came from physics and from the patient development of technologies that could detect light our eyes cannot process. Infrared light, electromagnetic radiation with wavelengths longer than visible red, ranging from just beyond what the eye can see out to wavelengths 100 times longer, behaves differently in the presence of dust. The dust grains that scatter and absorb visible light so efficiently have a critical vulnerability. They are roughly the same size as the wavelengths of visible light, which is precisely why the interaction is so effective. When electromagnetic radiation encounters particles of similar size, it scatters strongly. This is the same physics that makes the sky blue and sunsets red. Shorter wavelengths of visible light scatter off atmospheric molecules more readily than longer wavelengths. But push the wavelength long enough into the infrared and the interaction with dust weakens dramatically. The mathematics of scattering shows that the efficiency drops roughly as the inverse of wavelength to the 4th power for particles much smaller than the wavelength being considered. Infrared light at 2 micrometers wavelength, just a few times longer than visible red, penetrates the same dust cloud roughly 10 times more effectively. At longer infrared wavelengths, the penetration improves further still. The cosmic fog that renders Stevenson 2-18 completely invisible to optical telescopes becomes semi-transparent at infrared wavelengths. What was a wall becomes a gauze. What was absolute darkness becomes a detectable signal. This is the physics that finally broke the star's long concealment. Through the 1990s and into the 2000s, a series of increasingly capable infrared surveys began painting a more complete picture of the stellar populations hiding behind galactic dust. The 2-micron all-sky survey, completed in 2001, detected infrared emission from sources across the entire sky, with greater sensitivity than anything before it. The Spitzer Space Telescope, launched in 2003, extended observations to mid-infrared wavelengths inaccessible from Earth's surface, where the planet's own atmosphere absorbs infrared radiation before it reaches ground-based detectors. Each new instrument added information. Each new dataset revealed previously invisible structure. But knowing that something is bright in the infrared is not the same as knowing how large it is. To measure the physical dimensions of a star, you need 2 things: its apparent angular size, how large it appears in the sky, expressed in fractions of a degree, too small for human language to carry naturally, and its distance. Without both, you have nothing but a bright dot. Distance measurement for a star 200,000 light-years away, buried in one of the most obscured regions of the galaxy, is not straightforward. The primary technique astronomers rely on is called parallax, measuring the tiny shift in a star's apparent position as Earth moves from one side of its orbit to the other, a baseline of roughly 186 million miles. Nearby stars show larger shifts. Distant stars show smaller ones. The geometry is simple trigonometry. The execution at stellar distances requires measuring angular shifts smaller than the apparent size of a coin viewed from the opposite side of the planet. The Gaia Space Observatory, launched by the European Space Agency in 2013, changed what was possible. Gaia spent years tracking the positions of nearly 2 billion stars, with extraordinary precision building a catalogue of distances that transformed stellar astronomy. For stars in obscured regions like the direction of Stevenson, Gaia's infrared sensitivity allowed distance measurements that no previous instrument could achieve. When researchers combined Gaia distance data with brightness measurements from infrared surveys and applied the theoretical relationships connecting a star's temperature, brightness, and radius that stellar physics has refined over a century, the result was a number that required several readings before it settled into comprehension. 2,150 solar radii, give or take several hundred, depending on the methodology and the assumptions baked into the atmospheric models used to connect observed brightness to physical size. The uncertainty is real, and scientists are honest about it. Different teams using different techniques arrive at estimates ranging from roughly 1800 to 2400 solar radii. But even the conservative end of that range sits comfortably above every other measured star. The central estimate 2150 represents the current best consensus. What does that number mean in terms a human mind can hold? We will spend the next chapter trying to answer that. And I warn you now, every analogy will fall short. Every comparison will fail at some point. The number is simply too large for human intuition to process cleanly. But we will try anyway, because trying is what understanding requires. The star is real, the measurements are confirmed. The largest known stellar object in the observable universe burns tonight invisible 200,000 light-years away, and we have found it. There is a particular kind of failure that happens when human minds encounter numbers beyond a certain size. The failure is not ignorance. It is not stupidity. It is something more fundamental, a limit built into the architecture of cognition itself. We evolved to navigate a world measured in feet and miles, in minutes and years. We did not evolve to feel the difference between a million and a billion, between 1,000 solar radii and 2,000. The numbers become sounds, symbols on a page. They lose their weight, so we do not begin with the number. We begin somewhere smaller and we build. Pick up a basketball, hold it in your hands, feel the weight of it, the curve of the surface against your palms. A standard basketball measures roughly 9.5 inches across, just under a foot in diameter. Now set it on a table in front of you and let it represent our sun. Not a model of the sun, not a diagram. The sun itself, compressed, every one of those 865,000 miles of stellar plasma and nuclear fire, squeezed into 9.5 inches of rubber and air. On this scale, Earth is a small pebble, about the size of a ballpoint pen's tip. It orbits the basketball sun at a distance of roughly 75 feet, about the length of a modest house end to end. Mars orbits at around 115 feet out. Jupiter, the largest planet in this solar system, would be a marble-sized sphere, about 390 feet from the basketball. This is the solar system you live in, scaled down to something you can walk through. Now take that basketball and set it beside what Stevenson 2 to 18 would look like on the same scale. On the scale where our sun is a basketball, 9.5 inches across, Stevenson 2 to 18 is a sphere approximately 1700 feet in diameter. Pause on that. Not 1700 inches. Not 1700 feet across from edge to edge on a flat surface. A sphere. A ball of stellar material on a scale where the sun is a basketball. that stands 1700 feet tall, 1700 feet wide, 1700 feet deep. That exceeds the height of the Empire State Building. It exceeds the height of the Burj Khalifa, the tallest structure humans have ever built. It is a sphere taller than any skyscraper on Earth. A basketball sitting next to a structure larger than the tallest building in the world. That is the size comparison between our Sun and the largest known star in the observable universe. But diameter is only the beginning. Volume does not scale linearly. When you double the diameter of a sphere, you increase its volume by a factor of 8, because volume scales with the cube of the radius. When you increase the diameter by a factor of 2150, as is the case with Stevenson 2 to 18, compared to our Sun, volume increases by a factor of roughly 10 billion. 10 billion suns could fit inside this single star. Written as a number 1, 0.00000000000, 10 digits. If you tried to count to 10 billion at the rate of one number per second without sleeping, without stopping, without eating, it would take you 317 years. You would start counting in the present century. Your count would not finish until well into the 4th century from now. Every second of every day for 3 centuries, and you still would not have counted the number of suns that fit inside Stevenson 2 to 18. Now consider what the diameter alone means in physical terms. The actual diameter of Stevenson 2 to 18, not the basketball model, but the real star, measures approximately 1.87 billion miles. Write that out. 187,000,000,000 miles. A commercial airplane flying at 500 miles per hour, traveling in a straight line across this star's diameter, would take over 4,000,000,000 years to complete the crossing. 4,000,000,000 years. Modern humans, anatomically identical to you in every meaningful way, capable of the same thoughts, the same feelings, the same capacity for wonder, emerged in Africa roughly 3,000,000 years ago. The flight across Stevenson 2 to 18 would have begun before our species existed, and it would still be underway. The entire span of human existence on this planet, from the first Homo sapiens to look up at the stars and wonder, to you, reading these words right now, would not be long enough to cross this star at the cruising speed of a passenger jet. Every civilization that has ever risen and fallen, every language ever spoken, every war ever fought, every song ever sung, every child ever born, and every person ever mourned, all of human history, from beginning to present, not enough time to fly across one star. Light itself, the fastest thing the universe permits traveling at 670 million miles per hour, requires approximately 2 hours and 40 minutes to cross the diameter of Stevenson 2 to 18 from one edge to the other. The light leaving one side of this star right now will reach the other side before most people finish a single workday. For comparison, light crosses our sun's diameter in just under 5 seconds. 5 seconds versus 2 hours and 40 minutes. Those two numbers held together carry the scale more honestly than any diagram. Now we arrive at the comparison that tends to produce something close to genuine disorientation, the moment where the abstract becomes visceral and the mind reaches a boundary it cannot comfortably cross. Imagine that Stevenson 2 to 18 is placed at the center of our solar system. Its core sits where the sun currently burns, and we ask a simple question: what survives? Mercury is the closest planet to the sun, orbiting at an average distance of roughly 36 million miles. The surface of Stevenson 2 to 18 extends to approximately 935 million miles from its center, in every direction. Mercury does not merely become uninhabitable. Mercury does not merely get consumed by stellar radiation. Mercury ceases to exist as a separate object. It is inside the star, beneath the surface. Deep within the stellar interior, somewhere in the layers of hot plasma and convective gas, where the pressure alone would crush any structure we could imagine into its constituent atoms. Venus, at 67 million miles from the sun, gone. Inside the star, Earth, 93 million miles from the sun, the planet that has hosted every living thing in the history of life. Every ecosystem, every ocean, every mountain range, every city, every person who has ever drawn breath inside the star. Mars at 142 million miles. Gone. The asteroid belt, that vast ring of rocky fragments orbiting between Mars and Jupiter, containing millions of objects ranging from dust grains to dwarf planets. All of it inside the star. Jupiter, the largest planet in this solar system. A world so massive, it contains more material than all the other planets combined. A gas giant with a great red spot. A storm system that has been raging longer than humans have been doing science, and 95 known moons. Jupiter orbits at an average of 484 million miles from the Sun, inside the star. Saturn is the first object that survives. It orbits at an average of approximately 886 million miles from the Sun, which places it just barely beyond the surface of Stevenson 2 to 18, depending on the star's exact radius at any given moment, because red supergiants pulsate, expanding and contracting over cycles lasting years. During maximum expansion, Saturn's orbit might graze the stellar atmosphere. During contraction, it might sit just above a churning sea of plasma. From Saturn, if Saturn could be observed in this scenario, the star would not be a point of light in the sky. It would not be a disk the way the Sun appears as a disk from Earth. It would be a wall. A red wall filling roughly half the visible sky in every direction, horizon to horizon, and beyond an unbroken expanse of dim crimson light, so vast that the concept of daytime would lose all meaning. There would be no horizon where space begins. There would only be the star and the small arc of darkness visible above it, the thin sliver of universe not yet swallowed by that enormous surface. Uranus and Neptune would survive as well, orbiting in the cold and the red-tinged dark beyond the stellar surface. But from their surfaces, the star that replaced the Sun would fill the sky, the way nothing in our experience fills a sky. Not a sun, a presence, an environment, a red infinity extending in every direction below you and to the sides, with only the dome of space above, offering any reminder that a universe exists beyond this one overwhelming object. Consider for a moment what this means for the ordinary experience of light. The warmth you feel from sunlight on your skin results from a star 93 million miles away, a star whose surface temperature reaches nearly 1,000 degrees Fahrenheit, a star that occupies less than half a degree of arc in the sky, a tiny circle of white-yellow fire that you cannot look at directly without damaging your eyes within seconds. From a planet orbiting Stevenson 2 to 18 at the same distance, Earth orbits the Sun, a distance that would place you deep inside the stellar interior, far below the surface, which makes this comparison hypothetical. The experience of the star would be nothing like sunlight. It would be something for which human language has no adequate word. Every direction you looked would show you stellar surface, not sky, surface. The surface of a star that extends in every direction farther than you could travel in a human lifetime. There are no planets orbiting Stevenson 2 to 18 at any distance that would permit life as we understand it. The star's luminosity bathes surrounding space in radiation, intense enough to prevent stable planetary atmospheres from forming or persisting. Its stellar winds carry material outward at velocities that would strip any planetary surface clean of lighter compounds within geological timescales. And the star will not exist long enough for the slow processes of planetary formation and biological evolution to take hold in any case. But the hypothetical clarifies the scale in a way that raw numbers cannot. We are not talking about a large star. We are talking about an object that makes the word large feel inadequate, a word too small for what it is asked to describe. The mass of Stevenson 2 to 18, a number that might seem relevant here but will surprise you, falls somewhere between 15 and 25 solar masses. The star that dwarfs our Sun by a factor of 2, 150 inches radius by a factor of 10 billion in volume, does not outweigh it by a corresponding amount. Our Sun contains one solar mass by definition. Stevenson 2 to 18 contains perhaps 20 times the mass, 10 billion times the volume. This apparent paradox, enormous volume, modest mass, is the key to understanding what red supergiants actually are. That density mismatch, that staggering imbalance between size and weight, is not an anomaly. It is the defining characteristic of the most extreme class of stellar objects known to exist. If you took the mass of Stevenson 2-18 and spread it evenly through its volume, the resulting density would be roughly 10 million times less dense than the air you are breathing right now. The average interior of the largest known star in the observable universe is a better vacuum than most laboratory equipment on Earth can produce. A cubic meter of material taken from an average region inside this star would contain less matter than a cubic meter of the near vacuum between planets in our solar system. And yet from a distance it glows. It outshines nearly 500,000 suns. The light that eventually makes its way out of that tenuous, nearly empty vastness carries enough energy to outshine most stars in the galaxy on its own. This is the nature of the thing we have found. Not a dense furnace burning hot and bright in a compact space. Something stranger. A ghost of stellar materials spread across a volume that swallows solar systems glowing with the deep red light of a surface. Too cool for blue, too vast for silence, too extreme for the vocabulary we built to describe ordinary stars. The Stevenson 2 cluster that houses this giant contains at least 26 other red supergiants, making it one of the most remarkable concentrations of extreme stellar objects in the Milky Way. The entire cluster spans roughly 6 light-years across. That is smaller than the distance between our Sun and its nearest stellar neighbor. Within a volume that would fit between us and Proxima Centauri, 26 dying giants burn through their final fuel alongside the record holder. The cluster is not merely home to an extreme star, the cluster is itself a population of extremes, a brief and violent gathering of massive stars, all caught at the same late stage of their lives, all racing toward the same inevitable end. We observe them now because we happen to live at the right moment in their evolution. In 1,000,000 years, most of them will have exploded. The cluster will be unrecognizable, a scattered field of neutron stars and black holes surrounded by expanding shells of enriched gas. We caught them just in time, and we almost missed them entirely. For the whole of human history prior to infrared astronomy, this cluster was invisible. The dust was too thick. The technology did not exist. The light that left Stevenson 2-18 20,000 years ago, when human beings were still painting animals on cave walls in southern France, when the great ice sheet still covered much of the northern hemisphere, when the entire edifice of civilization that produced the telescopes used to detect this star was still unimaginably far in the future. That light passed through the galaxy, through the dust clouds, and arrived at Earth without anyone capable of recording it. Now we can. And what we have recorded changes everything about how we understand the upper boundary of stellar possibility. The largest known star in the observable universe was hiding in plain sight, in a direction that millions of human eyes have looked at on summer nights for as long as our species has existed. Invisible, waiting. We found it with infrared light and patient science and the accumulated technological inheritance of centuries of astronomical work. What we found was a star that could swallow the world you stand on without noticing. There is a question worth sitting with before we go further. If a star exists, that could swallow our entire inner solar system. A star burning with the power of 4,400,000 suns radiating energy across a surface 4 million times larger than our own. How is it possible that humanity spent its entire history from the first human to look up at the night sky to the invention of the telescope to the launch of the first space missions completely unaware of its existence? The answer is not that the star is far away. 20,000 light-years is distant by human standards, but it is well within the range of stars catalogued by astronomers for centuries. The Milky Way extends roughly 1,000,000 light-years in diameter. Stevenson 2-18 sits within the inner third of that span, practically a neighbor in galactic terms. We have detected stars in other galaxies, entirely objects, millions of light-years away. Distance alone does not explain the concealment. The answer is that the universe placed a wall between us and it, and that wall is made of something so ordinary, so unremarkable in everyday experience, that its significance in an astronomical context is easy to underestimate. Dust. not the dust that accumulates on shelves or drifts through sunlit rooms. Interstellar dust, microscopic grains of silicate minerals, carbonaceous compounds, and complex molecules that form in the outer atmospheres of dying stars and drift outward over millions of years, accumulating in the cold spaces between suns. These grains measure roughly 1 micrometer, across about 1/100th the width of a human hair. Individually, each grain is trivially small, but space is vast, and the processes that create dust have been operating for billions of years. In certain directions, particularly toward the inner galaxy, toward the dense spiral arms and the crowded regions near the galactic center, these grains accumulate into clouds of genuinely extraordinary opacity. The line of sight from Earth to Stevenson, 2 to 18, passes through the Scutum Centaurus arm, one of the major spiral arms of the Milky Way that lies interior to our own Orion arm. It passes through multiple dust lanes associated with the galactic bar, the elongated central structure of stars and gas that dominates the inner Milky Way. It passes through regions of dense molecular gas, where new stars are actively forming, surrounded by the dust from which they coalesce. Layer after layer of obscuring material, each adding its contribution to a cumulative extinction that reaches approximately 20 magnitudes in visible light by the time you account for all of it. 20 magnitudes means the star appears 100 million times fainter in visible wavelengths than it would appear without the intervening dust. A star, radiating with the power of 4,000,000 suns, dimmed by a factor of 100 million, becomes invisible. Not merely difficult to detect, not merely faint, invisible. No optical telescope ever built pointed in that direction would record a single photon from Stevenson to 18 inches visible wavelengths. The photons leave the star. They travel for 20,000 years. They arrive at Earth's location, having traversed the galaxy. And then they encounter the final thin layer of Earth's atmosphere and our instruments. But none of that matters, because they were absorbed and scattered thousands of light years earlier, long before they came anywhere near us. The star is shouting. We simply cannot hear it in the frequencies we evolved to detect. Understanding why infrared light penetrates where visible light cannot requires returning to the physics of how electromagnetic radiation interacts with small particles. When a photon of light encounters a dust grain, what happens depends critically on the relationship between the photon's wavelength and the grain's size. When the wavelength and the grain size are comparable, both roughly 1 micrometer, the interaction is efficient and strong. The photon can be scattered in a new direction or absorbed entirely and re-emitted as heat. Visible light has wavelengths between roughly 0.4 and 0.7 micrometers, right in the range where dust-grain interactions are most effective. This is not a coincidence. It reflects the fact that our eyes evolved to detect the wavelengths most abundantly produced by our particular star, and those wavelengths happen to sit in the range where interstellar dust is most effective at blocking them. Infrared light has longer wavelengths. Light at 2 micrometers wavelength, just slightly longer than the reddest visible light, interacts with dust grains far less efficiently. The mathematical relationship between wavelength and scattering efficiency means that at 2 micrometers, dust scatters radiation roughly 10 times less effectively than at visible wavelengths. Push to longer infrared wavelengths, 5 micrometers, 10 micrometers, 20, and the penetration improves further still. The cosmic fog that stops visible light cold becomes semi-transparent at infrared wavelengths. The 20 magnitudes of extinction that renders Stevenson 2 to 18 invisible to optical telescopes drops to perhaps 2 or 3 magnitudes in the near-infrared. A star dimmed by a factor of 100 million in visible light is dimmed by only a factor of perhaps 6 or 10 at 2 micrometers. The concealment is not perfect, but it is reduced from absolute to manageable. This is why Stevenson 2 to 18 was found not by the grand optical observatories that have defined astronomy for centuries, but by a new generation of instruments built specifically to see in wavelengths the human eye cannot process. The history of how we found this star is in miniature, the history of how astronomy learned to see beyond the visible. Charles Bruce Stevenson's catalogue work in 1990 used early infrared detectors that were, by modern standards, crude instruments. The technology of infrared detection had been developing since the mid-20th century, driven largely by military applications, heat-seeking missiles, night vision systems, thermal imaging for surveillance. The astronomical community borrowed and adapted these technologies, fitting them to telescope focal planes and cooling them to cryogenic temperatures to reduce the thermal noise that would otherwise overwhelm faint astronomical signals. The earliest infrared astronomical surveys in the 1980s had sensitivities and resolutions that would seem almost quaint compared to what came after. But they were real, they worked, and they began revealing a population of astronomical objects that had been completely invisible to the entire prior history of the discipline. Stevenson's 1990 catalogue was one product of this era. He was working with the tools available capable enough to detect that something bright in the infrared existed in the direction of what would eventually be named Stevenson 2, but not capable of determining what it was, how far away it sat, or what physical properties it possessed. The catalogue entry was a flag planted in uncertain territory. Here is something. Someone will need to come back and understand it. That understanding came in pieces over the following decades. The 2-micron all-sky survey, known by its abbreviation 2MASS, completed its observations in 2001 after 4 years of systematic work. 2 ground-based observatories, one in Arizona and one in Chile, scanned the entire sky at 3 infrared wavelengths, building a catalogue of nearly 500 million point sources and more than 1 million extended objects. The survey's sensitivity and uniformity transformed infrared astronomy the way the Palomar Sky Survey had transformed optical astronomy decades earlier, by providing a comprehensive baseline against which discoveries could be measured and objects could be located. 2MASS could not resolve the individual stars in Stevenson 2 with precision, but it placed better constraints on their infrared brightnesses, and it provided a reference framework that subsequent more detailed studies could build upon. It was one more layer of information added to an accumulating picture. The Spitzer Space Telescope, launched by NASA in August 2003, represented a qualitative leap. Spitzer observed at mid-infrared wavelengths from roughly 3 to 160 micrometers that are completely absorbed by Earth's atmosphere and therefore inaccessible to ground-based observatories. To function at these wavelengths, the telescope itself had to be cooled to temperatures approaching absolute zero, preventing its own thermal emission from swamping the faint signals from astronomical sources. Spitzer achieved this through a combination of liquid helium cooling in its orbit placed not around Earth but in a solar orbit, trailing behind our planet, drifting slowly away from us over years in a location where the cold of space could assist the cooling systems. From this vantage point, Spitzer spent years observing the most obscured regions of the galaxy, revealing stellar populations hidden from every previous instrument. Its observations of the Stevenson 2 cluster provided detailed mid-infrared photometry that further constrained the physical properties of the cluster's stars and the circumstellar material surrounding them. Spitzer could see the dust shells ejected by the red supergiants, glowing in thermal emission material that had left the stars thousands of years earlier, now drifting outward and cooling, still radiating faintly at wavelengths corresponding to its current temperature. But the critical missing piece remained distance. All the brightness measurements in the world could not convert angular size to physical size without knowing how far away the object sat. And measuring the distance to a star in one of the most obscured and crowded regions of the inner galaxy was, for most of astronomical history, essentially impossible. The technique of parallax, measuring the tiny apparent shift in a star's position as Earth moves from one side of its orbit to the other, works beautifully for nearby stars. The closer the star, the larger the shift, and the more precisely it can be measured. For stars within a few hundred light-years, ground-based parallax measurements achieved milliarc-second precision, useful numbers, real distances. For stars at 20,000 light-years, the parallax shift becomes approximately 100 micro-arcseconds, 100 millionths of a degree. For comparison, a human hair viewed from 30 miles away subtends roughly that angle. No ground-based telescope looking through the blurring effects of Earth's atmosphere could measure shifts this small. The distances remained estimates inferred from theoretical models and statistical arguments, rather than direct geometric measurement, carrying uncertainties that propagated directly into uncertainty about physical stellar sizes. The Gaia Space Observatory changed this. Launched by the European Space Agency on the 19th of December 2013, Gaia was designed from the ground up to solve the distance problem across the entire galaxy. Its mission was straightforward in concept and extraordinarily difficult in execution. Measure the positions and motions of nearly 2 billion stars, with precision approaching micro-arcseconds. To achieve this, the spacecraft carried 2 telescopes pointed in directions separated by a fixed angle, continuously scanning the sky and recording the positions of stars relative to each other and relative to a framework of extragalactic sources whose distances were known from other methods. The precision required was staggering. Gaia's detectors needed to measure stellar positions to accuracies corresponding to roughly the apparent size of a human hair, viewed from the distance of the Moon. The spacecraft's thermal stability had to be maintained to within millionths of a degree. The data processing required algorithms capable of simultaneously solving for the positions, parallaxes, and proper motions of billions of objects in a system of equations of extraordinary complexity. It worked. Gaia's data releases beginning in 2016 and continuing through subsequent years transformed stellar astronomy as thoroughly as any development since the invention of spectroscopy in the 19th century. For the first time, distances to stars throughout much of the Milky Way could be measured directly rather than inferred. For obscured regions like the direction of Stevenson, too, where theoretical distance estimates had carried uncertainties of 30% or more, Gaia provided constraints that were qualitatively more reliable. When researchers combined Gaia parallax measurements with the accumulated infrared photometry from 2 mass Spitzer, the Wide-Field Infrared Survey Explorer, and ground-based observatories, along with theoretical stellar atmosphere, models developed over decades of careful work. The physical dimensions of the Stevenson 2 cluster's member stars began to resolve from estimates into measurements. The result for the star now designated Stevenson 2-18 was approximately 2150 solar radii. Depending on which model atmosphere is used, which dust extinction law is applied, which parallax measurement is adopted, the number shifts. It might be 1900. It might be 2300. The uncertainty is real, and researchers are transparent about it. But across the full range of reasonable assumptions, the star remains the largest known object of its type. The error bars are large enough to matter for precision work, but not large enough to displace this star from the record. There is something worth pausing on here. The measurement of Stevenson 2-18 size did not happen in a single moment of discovery. It accumulated, layer by layer, decade by decade, instrument by instrument. Stevenson's 1990 catalogue entry, the 2 mass survey, Spitzer's mid-infrared observations, Gaia's parallax revolution. Each contribution was made by different teams of scientists working on different timescales, often without any awareness that their particular piece would eventually become essential to determining the dimensions of the largest known star in the observable universe. This is how science actually works. Not as a sequence of dramatic revelations handed down by solitary geniuses, but as an accumulation of incremental contributions, each one building on the work of predecessors, each one expanding what the next generation can ask. Answer: Stevenson himself, the astronomer who made the initial catalogue entry in 1990, did not discover the largest star. He found a flag in uncertain territory. Dozens of researchers who came after him over more than 30 years did the work of understanding what that flag marked. The discovery belongs to all of them, and to the institutions that built their instruments, and to the generations of physicists and engineers whose work made those instruments possible. The cluster itself, Stevenson 2, deserves attention as an object of wonder independent of its record-holding member. It contains at least 26 confirmed red supergiant stars, possibly more depending on how the cluster boundaries are defined and which membership criteria are applied. This concentration is extraordinary. Red supergiants are rare objects under any circumstances. They represent a brief phase in the lives of only the most massive stars, lasting perhaps a few 100,000 years out of total stellar lifetimes. measured in tens of millions of years. Finding one in isolation requires surveying enormous volumes of space. Finding 26 inches, a single gravitationally bound cluster, spanning only 6 light-years, suggests a common origin, a burst of star formation that occurred roughly 20 million years ago, producing a population of massive stars that have now all evolved to approximately the same late stage of their lives. The entire cluster would fit in the space between our Sun and its nearest known stellar neighbor, 6 light-years, the distance that light covers in 6 years. That is the volume within which 26 dying giants and dozens of smaller companion stars crowd together, each one a furnace burning through its final fuel, each one approaching the explosive death that awaits every object of its kind. The fact that they are all at approximately the same evolutionary stage reflects their common age. When the molecular cloud that gave birth to Stevenson 2 collapsed, triggered perhaps by the shockwave from a nearby supernova, or by the gravitational perturbation of a passing gas cloud, or by some other mechanism that remains unidentified, the stars that formed from it all emerged at roughly the same moment. They shared the same birth, and so they share the same approximate age. And because stellar evolution is so thoroughly determined by mass stars of similar mass that formed at the same time evolve along similar tracks and arrive at similar stages at similar times, we are observing Stevenson 2 during a narrow window when its most massive members have all reached the red supergiant phase but have not yet exploded. The window is perhaps 1 million years wide within a total cluster age of 20 million years. We observe it during the 5% of its existence when this configuration is possible. In geological terms, this is not a coincidence of improbable rarity, but in the context of astronomical observation, where the history of careful sky surveys spans only a few centuries, finding a cluster at exactly this stage is a matter of fortune. The next 1 million years will see this cluster transformed. One by one, its red supergiants will reach the endpoint of nuclear burning. Their iron cores will exceed the mass threshold that prevents further support, and they will collapse. Each collapse will trigger an explosion. Each explosion will scatter enriched material across light years of surrounding space, heating nearby gas, potentially compressing molecular clouds in the cluster environment, possibly triggering new generations of star formation while simultaneously disrupting others. In 1 million years, Stevenson 2 will be unrecognizable. The current configuration, this remarkable gathering of extreme objects caught at the last stage of their brilliance, will be gone. What remains will be a scattering of compact remnants, neutron stars, possibly black holes, surrounded by the cooling debris of multiple supernova explosions. We caught this cluster at the one moment in its long history when this particular view was possible. There is a broader lesson embedded in this. Every object we observe in the universe is observed at a specific moment in its history. The light reaching our telescopes tonight departed its source at some point in the past for Stevenson 2 20,000 years ago. We see not what exists now, but what existed then, frozen in the photons that have been traveling toward us ever since. The star that holds the record tonight might not exist in its current form at this moment in cosmic time. Dram, dime, drime. The explosion that will end it already occurred with the light from that event still crossing the 20,000 light-years that separate us. We cannot know. The finite speed of light ensures that our view of the universe is always a view of the past, always a collection of snapshots taken at different moments, assembled into a picture that we call the present. But that is really an elaborate collage of history. Stevenson 2-18 burns tonight in our data, in our measurements, in the infrared photons that were recorded by instruments built by human hands, using principles worked out by human minds over centuries of patient inquiry. Whether it still burns in reality, whether the star itself persists at this moment 20,000 years after the light we observed departed, is a question the universe has answered, but has not yet told us. 20 million years ago, the star that would become Stevenson 2-18 did not exist. In its place, there was a cloud, a vast, cold, slowly rotating mass of hydrogen and helium gas mixed with traces of heavier elements forged in previous generations of stars that had already lived and died before this solar system formed. The cloud was not uniform. It had denser regions and thinner regions, currents and eddies, shaped by the gravitational interactions of the galaxy around it. And in one particular region of that cloud, something happened. A perturbation, a compression, a slight increase in density that crossed a threshold, and gravity took over. The collapse began. In the early stages, it was imperceptibly slow. The cloud contracted over hundreds of thousands of years, its central regions growing denser and hotter as gravitational potential energy converted to heat. The gas that fell inward collided with other infalling gas and released energy. The center brightened. Pressure built. For a time, the radiation pressure pushing outward nearly balanced the gravitational pull drawing material inward, and the collapse slowed. But the cloud was massive enough, perhaps 30 to 40 times the mass of our Sun, that gravity ultimately won every local negotiation. The protostar at the center grew hotter, denser, more luminous. The surrounding envelope of infalling material began to glow, heated by the radiation from below. Jets of material erupted from the poles, carrying away angular momentum and allowing the central object to continue contracting without spinning itself apart. Disc-shaped structures formed in the equatorial plane as material with too much angular momentum to fall straight inward settled into orbit and spiraled slowly downward. Then, the core temperature crossed 10 million Kelvin. Hydrogen nuclei protons, bare atomic nuclei stripped of their electrons by the extreme heat, began moving fast enough to overcome the electromagnetic repulsion between them and approach closely enough for the strong nuclear force to bind them together. 4 protons fused into one helium nucleus, releasing the energy equivalent of the small mass difference between reactants and products. Einstein's equation E equals mc squared converted a tiny fraction of mass into an enormous quantity of energy. A star was born. The nuclear furnace ignited, and the outward radiation pressure balanced the inward gravitational pull for the first time. The collapse halted. Hydrostatic equilibrium established itself. The protostar became a star in the full astronomical sense, a self-sustaining nuclear reactor held in shape by the tension between two forces that would remain locked in this equilibrium for millions of years. The star that emerged from this process looked nothing like what we observe today as Stevenson 2-18. It was blue, compact, ferociously hot. Its surface temperature exceeded 20,000 Kelvin, more than 3 times hotter than our Sun's surface, which itself reaches approximately 5,700 Kelvin. At 20,000 Kelvin, the star radiated predominantly in ultraviolet wavelengths, producing light our eyes cannot detect, but which would have been deadly to any unprotected chemistry, resembling biology within distances measured in light years. The star's luminosity during this early phase already exceeded tens of thousands of suns, not because it was large, but because it was so extraordinarily hot that each square meter of its surface radiated enormous amounts of energy. Its physical size during this main sequence phase was perhaps 10 to 20 times the Sun's diameter, enormous by terrestrial standards, a sphere of stellar plasma large enough to swallow dozens of Earths. But compared to what it would eventually become, it was compact, concentrated, a fierce blue point radiating in a direction the sky found difficult to ignore, but that interstellar dust would eventually conceal from the rest of the galaxy. This is the version of Stevenson 2-18 that burned for the vast majority of its existence, not the red monster we catalogue today, the blue giant. The hot, compact, ultraviolet bright furnace that consumed hydrogen in its core at rates our Sun will never approach living fast in the way that only the most massive stars can live. The physics governing how quickly a star burns through its hydrogen comes down to a single relationship that counterintuitive enough to deserve careful examination. You might assume that a star with 30 times more hydrogen than our Sun would live 30 times longer. More fuel, more time. The logic seems sound. It is wrong. Massive stars do not merely burn their fuel, they incinerate it. The reason is temperature. Gravity compresses the core of a massive star to higher densities and temperatures than occur in less massive stars, because more mass means more gravitational force pressing inward, which requires higher internal pressure to resist, which requires higher temperature to generate. The core temperature of a young Stevenson 2 to 18 during its hydrogen burning phase was probably around 40 million Kelvin, roughly 3 times higher than our Sun's core temperature of 15 million Kelvin. This temperature difference matters because nuclear fusion rates do not scale linearly with temperature. They scale exponentially. The dominant hydrogen fusion process in massive stars, the carbon-nitrogen-oxygen cycle, which uses carbon, nitrogen, and oxygen nuclei as catalysts to facilitate hydrogen fusion, proceeds at a rate proportional to approximately the 16th power of temperature. This means that if you double the core temperature, the fusion rate does not double. It increases by a factor of 2 to the 16th power, approximately 65,000. A slightly hotter core burns fuel at an explosively faster rate. The result is that Stevenson 2 to 18, despite having perhaps 30 times more hydrogen than the Sun, burned through its entire core hydrogen supply in roughly 10 to 15 million years. Our Sun, with its cooler core and slower fusion rate, will take 10 billion years to exhaust its hydrogen. The Sun has already been burning for approximately 4.5 billion years. It has another 5.5 billion years of hydrogen burning ahead. Stevenson 2 to 18 burned through the equivalent of its entire existence birth, to present roughly 20 times over in the time our Sun has already spent on the main sequence. Massive stars are not long-lived giants. They are brilliant, short-lived consumptions. Supernovae in waiting, born already racing toward their deaths. When the hydrogen in the core finally ran out, when the last proton-proton fusion reaction converted the final available hydrogen nuclei into helium, and the nuclear furnace that had sustained equilibrium for 10 million years sputtered and failed, the star found itself in a position of profound structural crisis. The energy source holding the star up was gone. Without radiation pressure to resist it, gravity asserted itself without opposition in the core. The helium ash that had accumulated there began to contract. Gravitational potential energy converted to heat as the core compressed. The temperature rose. The surrounding shell of hydrogen, still unburned, still capable of fusion, found itself subjected to the rising temperatures radiating outward from the contracting helium core below. It ignited. A shell of hydrogen burning ignited just outside the inert helium core, producing energy at rates exceeding what the original core fusion had generated. This shell burning changed everything about the star's structure. The increased energy output from the hydrogen shell could not escape the star as efficiently as before. The outer layers absorbed some of this energy and responded the only way physics permitted. They expanded. The star began to swell. Its surface retreated outward, cooling as it spread across a larger and larger area. The surface temperature dropped from 20,000 Kelvin toward 10,000, then 8,000, then 5,000, then lower still. The star was transforming. Not suddenly, not dramatically in human terms, but on timescales of thousands of years, the compact blue giant was becoming something else entirely. The expansion continued. The surface cooled further. At temperatures below roughly 4,000 Kelvin, something happens in the outer layers of a star that fundamentally changes how energy moves through it. The opacity of stellar material, how effectively it absorbs and blocks radiation, increases sharply as temperatures drop into a range where ionized hydrogen can recombine with electrons to form neutral hydrogen atoms. Neutral hydrogen absorbs radiation far more efficiently than fully ionized plasma. The outer layers of the cooling, expanding star became increasingly opaque. When radiation cannot move through material efficiently, convection takes over. Hot material rises, cool material sinks. Giant, churning cells of gas transport energy upward, the way boiling water moves heat from the bottom of a pot to the surface. In an ordinary star, like the Sun, convection operates in a well-defined outer zone, while radiation handles energy transport in the deeper interior. The convective envelope is a feature of the star's structure, important but bounded. In an expanding, cooling, massive star, approaching the red supergiant phase, the convective envelope deepens dramatically as temperatures drop. It eventually extends through most of the stellar volume, reaching from just above the nuclear burning shells all the way out to the visible surface. And convection, unlike radiation, has no natural size limit. A convective envelope can expand to whatever size is necessary to transport the energy flowing through it from below. As the energy output from the shell-burning regions increased, as the convective envelope deepened and extended, the outer layers of the star continued their outward retreat. The expansion that began with the exhaustion of core hydrogen continued, driven by convective transport of shell-burning energy for thousands of years. The star grew. Consider what this expansion looks like in physical terms. The compact blue giant, perhaps 15 times the Sun's diameter at its peak main sequence size, began swelling at rates that would seem imperceptible on human timescales, but were geologically rapid. Over hundreds of thousands of years, the outer layers retreated from a radius of perhaps 100 million miles outward to 1 billion miles, then further still. The surface temperature fell from 20,000 Kelvin to 10,000, to 7,000, to 5,000, to 4,000, to the approximately 3,200 Kelvin where it sits today, cool enough for simple molecules like titanium oxide and water vapor to form in the stellar atmosphere, cool enough to glow not white or yellow but deep red, cool enough that each square meter of the surface radiates far less energy than each square meter of our Sun, despite the star's total output exceeding nearly 500,000 suns. The paradox of the red supergiant is this: an object that produces 44,000,000 times as much energy as the Sun appears dimmer per unit surface area than our own star. The total power is staggering. The surface brightness is modest. The reason is that the total power spreads across a surface 4 million times larger, diluting the intensity the way a searchlight's beam dilutes as it expands with distance. If you could somehow stand near Stevenson 2-18, at a distance where the star subtended the same angle in the sky as our Sun does from Earth, you would not be blinded by its brilliance. You would see a vast red disk, dim and ruddy compared to the white-yellow intensity of our Sun. The thermal output at that distance would be enormous, the radiation environment lethal, but the visual impression would be of something more like a glowing coal than a burning point of fire. The star is simultaneously the largest source of energy in the local galaxy, and per unit area, one of the dimmest stellar surfaces known. This duality captures something essential about what red supergiants are. They are not simply large versions of ordinary stars. They are structurally different objects operating under different physical regimes, with properties that emerge from the extreme solution the universe found to the problem of transporting energy from a nuclear burning shell through an enormous convective envelope to a cool, diffuse surface. Inside Stevenson 2-18, as the outer envelope expanded to its current dimensions, the nuclear burning did not stop. It escalated. While the visible star was growing to swallow solar systems, its interior was undergoing a sequence of transformations of increasing desperation and increasing violence. Each transformation brought the star closer to the end that has been inevitable since it formed. The helium core, which had been contracting and heating since the exhaustion of core hydrogen, eventually reached temperatures high enough to ignite its own nuclear burning. At roughly 100 million Kelvin, helium nuclei, which carry twice the positive charge of hydrogen nuclei, and therefore repel each other twice as strongly, can finally approach closely enough for the strong force to bind them. 3 helium nuclei combine in a sequence of reactions to form carbon, 1, 2, releasing energy and continuing the process of stellar support. But helium burning is less efficient than hydrogen burning. Each helium fusion reaction releases less energy per unit mass than the corresponding hydrogen reaction. The furnace burns hotter and faster to compensate, consuming its fuel more rapidly. Where hydrogen burning in the core lasted 10 to 15 million years, helium burning lasted perhaps 1 million years, a tenth as long, the star racing faster through each successive fuel source, each phase shorter than the one before. The helium eventually ran out. Carbon and oxygen accumulated in the core contracted again, heating further. Carbon ignited at approximately 500 million Kelvin, fusing into neon and magnesium over timescales of perhaps a few thousand years. Neon burning followed, lasting just a few years. Oxygen burning at temperatures exceeding 1 billion Kelvin lasted perhaps a few months. Each successive burning phase occupied a smaller region, generated less energy per reaction, and lasted a fraction of the time of its predecessor. The star was running out of viable fuel sources with increasing urgency. The intervals between crises, between the exhaustion of one fuel and the ignition of the next, grew shorter. The nuclear evolution that had proceeded at a stately pace for millions of years was accelerating toward a conclusion. Deep within the star, the structure that had formed over this long evolutionary journey took the shape of concentric shells like the layers of an onion. At the center, an inert core of iron and nickel, the ash of silicon burning the final product that nuclear fusion can produce without consuming energy rather than releasing it. Surrounding that, a thin shell, where silicon fusion was converting the last silicon into iron at rates measured in days. Outside that, shells of oxygen burning, neon burning, carbon burning, helium burning, hydrogen burning, each shell thinner, each one operating at temperatures and densities extreme by any ordinary standard, each one separated from the next by boundaries where the composition and the physics changed abruptly. And surrounding all of it, surrounding the nuclear onion that fit within the volume of a small star, the vast red envelope, the enormous, tenuous, cool outer atmosphere that extended to 2150 solar radii and defined what Stevenson 2-18 looks like from the outside. The envelope barely aware of the drama unfolding in its interior. The communication between core and surface, limited by the sound crossing time, the time required for pressure waves to travel from center to photosphere, which in a star, this large measures in years. The surface we observe today reflects conditions in the core from years ago. What is happening in the core right now at this moment, as you encounter these words, is information that has not yet reached the photosphere, let alone traveled the 20,000 light-years to Earth. The outer atmosphere of Stevenson 2-18 possesses properties unlike anything in ordinary stellar experience. At the photosphere, the visible surface, the depth at which light can finally escape freely into space, the temperature is approximately 3,200 Kelvin. This is hot enough to glow visibly red. It is cool enough for molecules to survive. Spectroscopic observations of red supergiants reveal the signatures of titanium oxide, water vapor, and carbon monoxide in their outer atmospheres. These molecules would be destroyed instantly at the surface of our Sun, where temperatures of nearly 6,000 Kelvin prevent stable molecular bonds from forming. In the cool outer layers of Stevenson 2-18 chemistry operates in ways impossible for smaller, hotter stars. The density at the photosphere defies ordinary intuition from a different direction. The star is simultaneously enormous and nearly empty. The outer atmosphere, the visible surface, has a density roughly 1/1000th of Earth's atmospheric density at sea level. 1/1000th. The material forming the visible boundary of the largest known star is a better vacuum than most laboratory equipment on Earth can achieve. High vacuum chambers used in precision scientific experiments typically maintain densities millions of times higher than the photospheric density of Stevenson 2-18. The surface of the largest known star is essentially empty space. Yet this nearly empty material glows. The photons generated in deeper, denser regions scatter and interact through these diffuse outer layers, taking a convoluted path to freedom before finally escaping into the surrounding darkness. The molecular absorption in this cool, thin atmosphere shapes the emerging light, producing the spectral signatures that allow astronomers to measure the star's temperature and composition from 20,000 light-years away. The convection cells churning through the outer envelope of Stevenson 2-18 operate on scales that make the word massive seem inadequate. Individual convection cells, single rising columns of hot gas, and single sinking columns of cooler gas probably span distances of several astronomical units. 1 astronomical unit is the average distance from Earth to the Sun, 93 million miles. The convection cells in this star are larger than the distance between Earth and the Sun. Observations of nearby red supergiants like Betelgeuse, which sits only about 700 light-years from Earth and can be resolved in some detail by the largest existing telescopes, reveal exactly this kind of large-scale surface structure. Bright regions where hot material rises, dark regions where cooler material descends, a mottled, slowly shifting surface texture that changes configuration over timescales of months to years. Stevenson 2 to 18, too distant and too obscured for direct surface imaging, almost certainly displays the same phenomenon on even grander scales. The convection cells on its surface would each be larger than Jupiter's entire orbit. The star breathes in and out, not metaphorically. Red supergiants pulsate. They expand and contract over cycles lasting hundreds to thousands of days, driven by changes in how efficiently their outer layers absorb and release radiation. As the star compresses, slightly temperature rises in certain layers, which changes the opacity of the gas, which traps more radiation, which increases pressure, which drives expansion. Expansion leads to cooling, which changes opacity again in the opposite direction, which allows radiation to escape, which decreases pressure, which allows contraction to resume. The cycle repeats with rough regularity. For Stevenson, 2 to 18 pulsation periods probably span several years, given its enormous dimensions and low surface gravity. The radius at maximum expansion may exceed the radius at minimum by 10% or more. The variation in volume over a single pulsation cycle exceeds the total volume of our Sun many times over. The star is not a static object. It is a dynamic one, changing size, shedding material through stellar winds that carry millions of times more mass per year than our Sun's solar wind, ejecting shells of gas into the surrounding space that glow faintly in infrared as they cool and drift outward, building a circumstellar nebula, a cocoon of previously shed material that surrounds the star at various distances, each shell representing an epoch of enhanced mass loss frozen at the distance it has traveled since ejection. The question of how much longer this can continue brings us to a threshold that stellar physics approaches with the mathematical certainty of geometry. At the center of Stevenson 2 to 18, iron accumulates, and iron changes everything. Every element in the periodic table lighter than iron releases energy when fused into heavier elements. This is why stars can burn. Hydrogen releases energy when fused into helium. Helium releases energy when fused into carbon. Carbon into neon. Neon into oxygen. Oxygen into silicon. Silicon into iron. Each reaction powers the star, generating the radiation pressure that holds the outer layers against gravity. Iron is different. Iron, 5-6, the most common iron isotope, sits at the peak of what physicists call the nuclear binding energy curve. It is the most tightly bound nucleus that exists. Fusing iron into anything heavier does not release energy. It consumes it. The star cannot extract power from iron. Iron is the end of the line, the final ash, the point beyond which no further nuclear alchemy can hold back the weight of the star above. The iron core grows heavier with every passing day. Every silicon fusion reaction deposits more iron into the central regions. The core adds perhaps 1/10 of a solar mass per day during the silicon burning phase. Each gram of iron that accumulates is a gram that will never again contribute to holding up the star. The core is building toward a threshold, a mass limit calculated first by Supergiant Chandrasekhar in the 1930s, a young Indian physicist who worked out the calculation during a steamship voyage from India to England, staring at the equations until they revealed their answer, the Chandrasekhar limit, approximately 1.4 solar masses of iron, beyond which no known physical force can prevent gravitational collapse. The core of Stevenson 2 to 18 is approaching that limit. Whether it has already crossed it, whether the collapse that ends this star's life has already begun, is a question the universe has answered, but that the finite speed of light prevents us from knowing. The information about the current state of the core must travel outward through the stellar interior, through the envelope, through 20,000 light-years of interstellar space, and reach our detectors before we can know what is happening now. We see the star as it was 20,000 years ago. What is happening in its core at this moment in cosmic time? Whether the iron continues to accumulate, whether the threshold has been crossed, whether the collapse that will end the largest known star has already begun, we cannot say. We can only wait for the light to tell us. The iron core grows in silence. There is no signal visible from outside, No brightening, no dimming, no change in the slow red glow that has characterized this star for hundreds of thousands of years. The outer envelope continues its vast convective churning, its surface mottling with enormous rising and sinking cells of plasma, its stellar winds carrying material outward into surrounding space at their usual prodigious rates. From 20,000 light-years away, through infrared telescopes pointed at a small cluster of red stars in the direction of the inner galaxy, Stevenson 2-18 looks today essentially as it looked last year and the year before and 1,000 years before that. Below the surface, in a region occupying a volume smaller than Earth, at the center of an object larger than Saturn's orbit, the situation is different. The silicon-burning shell, a thin layer of material where silicon nuclei are fusing into iron group elements at temperatures exceeding 3 billion Kelvin, continues its work. Each reaction converts a small quantity of silicon into a slightly larger quantity of iron. Each gram of iron that accumulates in the core adds its weight to the gravitational burden that the core must bear. The core contracts slightly under this growing weight, heating as it compresses, the increased temperature accelerating the silicon fusion above it, which produces more iron, which adds more weight, which compresses the core further. The feedback is gentle at first, gradual. The core has been growing for days, for weeks. The silicon burning phase that began when oxygen burning exhausted itself. That transition happening perhaps a few months ago in the star's reference frame, though the information of that transition has not yet reached us, proceeds with mathematical inevitability toward a single number, 1.4 solar masses of iron, the Chandrasekhar limit, the boundary past which no known physics can hold. The core approaches this threshold the way a dam approaches failure under rising water. Everything appears stable until the moment it does not. When the iron core mass crosses the Chandrasekhar limit, the collapse begins, not gradually, not with warning signs visible from outside, not with the slow evolutionary transitions that characterized every previous phase of this star's long life. The collapse begins instantaneously, on timescales measured in milliseconds, driven by physics that operates with the indifference of mathematics applied to extreme conditions. The mechanism of support that has held the iron core against gravity is called electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state simultaneously. In the dense iron core, electrons are packed so tightly that they cannot be compressed further without violating this principle. The resulting pressure, not thermal pressure from hot gas, but quantum mechanical pressure from electrons resisting identical states, has been holding the core against gravity for the duration of the silicon burning phase. Above the Chandrasekhar limit, gravity overcomes even this. The gravitational force becomes strong enough to force electrons and protons together, converting them into neutrons and neutrinos through a process called electron capture. Each such reaction removes two electrons from the gas, two of the particles providing the degeneracy pressure. As more and more electrons disappear into neutrons, the pressure that was holding the core up diminishes. The core becomes less supported. It contracts. Contraction brings more material to higher densities. Higher densities accelerate the electron capture reactions. More electrons disappear, less support remains. The process runs away. Within milliseconds, the collapse that began with the first electron capture reactions has become a catastrophic implosion that no force in the core can arrest. Material falls inward at roughly a quarter of the speed of light, 75,000 kilometers per second. For comparison, the speed required to escape Earth's gravity is approximately 11 kilometers per second. The fastest spacecraft humans have ever launched traveled at roughly 70 kilometers per second at its peak velocity. The collapsing core material moves 1,000 times faster than the fastest thing we have ever built, and it is accelerating. The iron core, which occupied a volume roughly the size of Earth, approximately 8,000 miles across, collapses to a sphere 20 kilometers in diameter in approximately 1 second. Hold that. 1 second. The time it takes to read a short sentence. In that interval, an object containing more mass than our Sun compresses from the size of a planet to the size of a city. The density increases by a factor of roughly 100 trillion. The temperature reaches hundreds of billions of Kelvin. The conditions become unlike anything that exists anywhere else in the observable universe outside of black holes themselves. If you could somehow watch this from nearby, which would be instantly lethal in ways too numerous to enumerate, you would see nothing. The collapse is happening inside the star, beneath billions of miles of stellar material. The surface of Stevenson 2-18 continues, glowing its dim red glow completely unaware. The information that the core has collapsed is traveling outward as a pressure wave through the stellar interior at the speed of sound in stellar material, a few thousand kilometers per second. At that speed, it will take hours to reach the surface. For hours after the core collapses, the star looks exactly as it always has. The universe keeps its secrets well. At the moment the collapsing core reaches nuclear density, the density at which individual neutrons and protons are in direct contact with each other, pressed together as tightly as the strong nuclear force permits, something changes. Nuclear matter is not infinitely compressible. The strong force that holds atomic nuclei together becomes repulsive at extremely short distances, resisting further compression with enormous force. The collapsing core hits this nuclear floor like a rubber ball dropped onto concrete. It bounces. The bounce is not gentle. The kinetic energy of the infalling material, accumulated over the fraction of a second of freefall from Earth-sized dimensions to city-sized dimensions, converts instantaneously from inward motion to outward motion. A shock wave erupts from the newly formed proto-neutron star at the center and propagates outward through the overlying layers of still infalling material. This shock wave carries energy equivalent to roughly 10 to the 44 joules, a unit astronomers call 1 Bethe, named after Hans Bethe, the physicist who did foundational work on both stellar nucleosynthesis and supernova physics. 1 Bethe of energy. For comparison, our Sun will radiate approximately 4 times 10 to the 43 joules over its entire 10 billion year lifetime. The shock wave generated in the first milliseconds of the neutron star's formation carries energy comparable to a quarter of the Sun's entire lifetime output, generated in a fraction of a second. You would expect this to be enough to blow the star apart immediately. It is not. The shock wave stalls. As it propagates outward through the still infalling iron core material, it must disassemble every iron nucleus it encounters, breaking the tightly bound iron, 5-6 nuclei back into their constituent protons and neutrons. Each disassembly reaction consumes energy rather than releasing it. The shock loses energy with every iron nucleus it destroys, bleeding its momentum into nuclear dissociation like a wave breaking against a series of breakwaters. Within roughly 100 milliseconds, the shock has stalled at a radius of perhaps 100 to 200 kilometers from the center, far short of the stellar surface, far short of anything visible from outside. For decades, this stalling was the central unsolved problem in supernova physics. Computer simulations repeatedly showed the shock dying, the star failing to explode, all the infalling material collapsing onto the neutron star and forming a black hole in silence. But observed supernovae clearly did explode. Something was reviving the shock. Something was providing the additional energy needed to push it through the remaining material. The answer, established through decades of increasingly sophisticated three-dimensional simulations, involves the neutrinos. During the collapse, as electrons and protons merge to form neutrons, each reaction produces a neutrino, a particle so weakly interacting that it passes through ordinary matter essentially without resistance. Neutrinos can travel through a light year of solid lead without being stopped. They stream through Earth by the trillions every second from the Sun, and virtually none of them interact with any atom in the planet. They are, for most practical purposes, ghosts. In the first second after core collapse, the proto-neutron star releases approximately 3 times 10 to the 53 joules of energy in the form of neutrinos. This is not a small number. It is roughly 100 times the total energy our Sun will radiate over its entire lifetime. It is approximately the total gravitational binding energy of the neutron star released all at once as the core compresses to nuclear density. It is, in terms of raw energy output per unit time, the most luminous event the universe produces, short of the Big Bang itself. This neutrino luminosity exceeds the combined light output of every star in the observable universe, estimated at roughly 2 trillion galaxies, each containing hundreds of billions of stars for a duration of approximately 10 seconds. 10 seconds of neutrino emission, more energy than all the starlight in the observable universe combined, and virtually none of it interacts with anything. Virtually none. Not exactly none. In the dense region just outside the proto-neutron star, the matter density is high enough that even weakly interacting neutrinos deposit a small fraction of their energy, perhaps 1%, into the surrounding material. 1% of 3 times 10 to the 53 joules is still 3 times 10 to the 51 joules. Enough combined with turbulent convection and hydrodynamic instabilities that develop in the region behind the stalled shock to revive the explosion. The exact mechanism remains an active area of research. Three-dimensional simulations reveal that the revival is not smooth or symmetric. It involves chaotic flows, turbulent hot bubbles rising behind the shock, asymmetric energy deposition that pushes different parts of the shock outward at different rates. The explosion that emerges from this process is inherently asymmetric. The neutron star gets a kick from the asymmetric momentum of the explosion, potentially sending it flying through the galaxy at hundreds of kilometers per second. But the shock revives. It resumes its outward journey, and now it faces a very different challenge than it faced in the iron core. For a compact star, a blue supergiant, a Wolf-Rayet star, the shock would reach the surface within minutes. The dense, compact envelope offers relatively little volume to traverse. The breakout would be rapid and violent, producing a sharp ultraviolet flash visible across galactic distances. Stevenson 2-18 is not compact. The revived shock must travel through approximately 1.87 billion miles of stellar material. The hydrogen envelope of this red supergiant extends from the nuclear burning shells, sitting perhaps a few thousand kilometers above the neutron star, all the way out to the photosphere, nearly a billion miles distant. Even traveling at 10,000 kilometers per second, roughly 3% of the speed of light, this journey takes many hours. Hours during which the surface continues glowing exactly as it always has. Hours during which no observer anywhere in the galaxy has any indication that the largest known star is in the process of destroying itself from within. The shock travels outward. It heats the stellar material it passes through to temperatures of billions of Kelvin. In this extreme environment, nuclear reactions that cannot occur under normal stellar conditions proceed rapidly. The rapid neutron capture process, the R process, builds elements heavier than iron by adding neutrons to seed nuclei faster than radioactive decay can remove them. Gold forms, platinum forms, uranium forms, thorium forms. Every heavy element in the periodic table that cannot be synthesized in ordinary stellar burning is forged in the few seconds of extreme conditions behind the supernova shockwave. The gold in any jewelry you might be wearing was made this way. Not in this star, not yet, but in a star that underwent this same process before our solar system formed, seeding the molecular cloud from which the Sun and Earth eventually condensed with the heavy elements that would become the rocks, oceans, and eventually the living things of this world. When the shock finally reaches the surface of Stevenson 2-18, when it breaks through the photosphere after its long journey through the stellar interior, the star becomes visible. Not gradually, not subtly. Within hours of shock breakout, the star brightens by factors of billions. The surface material, accelerated by the passage of the shock wave, erupts outward at velocities reaching 10,000 to 30,000 kilometers per second. Material that was the outer atmosphere of a red supergiant an hour earlier is now expanding debris, carrying heavy elements synthesized in the explosion into the surrounding interstellar medium. The peak luminosity of the resulting supernova will reach several billion times the luminosity of our Sun. For a period of days to weeks, this single dying star will outshine every other star in the Milky Way combined. The Milky Way contains approximately 400 billion stars. One dying red supergiant temporarily produces more light than all of them together. We know what this looks like from a distance because we have seen it before. Not in our galaxy, no supernova has been observed in the Milky Way since 1604, before the invention of the telescope, but in a neighboring galaxy, close enough to study in detail. On the 23rd of February 1987, a blue supergiant star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way located approximately 168,000 light-years away, exhausted its core fuel and collapsed. The resulting explosion, designated supernova 1987A, became the brightest supernova observable from Earth since 1604 and the most studied supernova in the history of the discipline. Before the light arrived, something else did. At 7:35 inches the morning, universal time detectors designed to search for proton decay, massive tanks of purified water surrounded by light detectors buried deep underground to shield them from cosmic rays, began registering anomalous events. The Kamiokande 2 detector in Japan recorded 12 events in the span of 13 seconds. The IMB detector in Ohio recorded 8 events. The Baksan detector in the Soviet Union recorded 5 events. 25 subatomic particles detected across 3 facilities on opposite sides of the planet, within seconds of each other. They were neutrinos, arriving from the direction of the Large Magellanic Cloud, carrying the news of a stellar collapse 168,000 light-years away, traveling at nearly the speed of light, penetrating the entire mass of the Earth, without slowing down and depositing enough energy in those underground detectors to trigger the recording equipment. 25 particles from an explosion 168,000 light-years distant. This detection, representing perhaps 1 in 10 billion of the total neutrinos that passed through Earth, confirmed the theoretical predictions about core collapse physics that had been developed over decades. It earned a share of the 2002 Nobel Prize in Physics. For Stevenson 2 to 18, the numbers scale dramatically. The star sits 168,000 light-years from Earth, the same distance as supernova 1987A. No. Stevenson 2 to 18 is 2,000 light-years away, roughly 8 times closer. Neutrino flux falls off with the square of distance. 8 times closer means 64 times more neutrinos passing through each square meter of Earth's surface. Modern detectors are also far larger and more sensitive than those operating in 1987. The Super Kamiokande detector in Japan, the successor to the Kamiokande 2 that detected 1987A's neutrinos, contains 50,000 tons of purified water compared to the 3,000 tons of the original. The Ice Cube detector at the South Pole monitors a cubic kilometer of Antarctic ice, the largest neutrino detector ever constructed. If Stevenson 2 to 18 undergoes core collapse today, Super Kamiokande alone would register tens of thousands of neutrino events in the span of approximately 10 seconds. Ice Cube would register millions of individual signals. The data from a single galactic supernova would occupy researchers for decades. These neutrinos would arrive at Earth several hours before any electromagnetic brightening becomes visible, because the neutrinos escape the core within seconds of collapse, while light must wait for the shock wave to reach the surface. The Supernova Early Warning System, an international network connecting neutrino detectors worldwide, exists specifically to provide this advance notice. When a galactic supernova occurs, astronomers would receive an automated alert hours before the star begins to visibly brighten, allowing telescopes around the world to be pointed at the correct location before the show begins. Every major observatory on Earth would orient itself toward the constellation Scutum. Every space telescope with relevant capabilities would adjust its pointing. The gravitational wave detectors LIGO in the United States, Virgo in Italy, Cagra in Japan, would monitor for the asymmetric collapse dynamics that produce gravitational wave signals distinct from the clean chirps of merging compact objects. The world's scientific attention would focus on a single point in the sky, and there, in infrared wavelengths that can penetrate the dust, a star that humanity has known about for barely 3 decades would reveal the violence of its ending. The question of what the explosion leaves behind sits at the intersection of current research and genuine uncertainty. At the center of the expanding debris cloud where the neutron star formed in the first second of collapse, one of two things exists. Either a neutron star, city-sized, incredibly dense, supported against further collapse by neutron degeneracy pressure and the repulsive component of the strong nuclear force at nuclear densities, or a black hole formed if the collapsing material's mass exceeded what neutron degeneracy pressure can support. The dividing line between these outcomes falls somewhere around 2 to 3 solar masses of remnant material. Below that threshold, a neutron star survives. Above it, collapse continues until a black hole forms. For Stevenson 2 to 18, the answer is genuinely unknown. The star's initial mass of perhaps 25 to 40 solar masses has been reduced by stellar wind mass loss over millions of years, perhaps to 15 to 25 solar masses by the current epoch. The fraction of that mass that ends up in the collapsed remnant depends on how much the explosion successfully ejects versus how much falls back. Simulations disagree. Different explosion energies, different degrees of asymmetry, different assumptions about neutrino physics produce different remnant masses in different models. If a neutron star forms, it will be born spinning rapidly, perhaps tens or hundreds of times per second, because conservation of angular momentum amplifies the slow rotation of the original stellar core as it collapses by factors proportional to the square of the radius reduction. The original core, slowly rotating once every few months, becomes a neutron star, potentially spinning hundreds of times per second. Combined with the intense magnetic fields generated during collapse, this young neutron star would be a pulsar sweeping beams of radio emission across the sky, like a lighthouse as it spins. If Earth happens to lie in the path of that beam, we would detect a new pulsar within the expanding debris cloud of the supernova remnant. The Crab pulsar formed in the supernova observed by Chinese astronomers in 1054 AD still pulses 30 times per second, nearly 1,000 years later, powering a glowing nebula with its rotational energy. A pulsar from Stevenson 2 to 18 would begin its life spinning far faster, gradually slowing over centuries as magnetic braking converts rotational energy to radiation. If a black hole forms instead, the compact remnant will be invisible, except through its gravitational effects on surrounding material. Any gas that falls back toward the center after the explosion, rather than escaping into space, will spiral inward and form an accretion disk around the black hole. The friction within this disk heats material to extreme temperatures, producing X-ray emission detectable by orbiting observatories. The black hole itself emits nothing but its influence on surrounding matter, reveals its presence to instruments sensitive enough to detect the consequences. The expanding debris cloud from the explosion will carry between 10 and 20 solar masses of material outward into surrounding space at velocities of 10,000 to 30,000 kilometers per second. This material includes the hydrogen and helium of the former stellar envelope, the products of decades of nuclear burning in the various shells, and the heavy elements synthesized during the explosion itself, including the gold, platinum, uranium, and dozens of other heavy elements produced in the extreme conditions behind the shockwave. This enriched material will expand for thousands of years, sweeping up surrounding interstellar gas and gradually slowing as it transfers momentum to the material it collects. It will glow at multiple wavelengths as it cools X-rays from the shock-heated gas optical emission from recombining atoms, radio waves, from electrons spiraling in magnetic fields. Future astronomers equipped with telescopes we cannot yet imagine will observe this expanding remnant and read from its structure the story of the explosion that created it. In perhaps 1 billion years, the material ejected by Stevenson 2 to 18 will have mixed with the interstellar medium of the Milky Way and become incorporated into new molecular clouds. Those clouds will collapse to form new stars. Some of those stars will have planets. Some of those planets will have the heavy elements from Stevenson 2 to 18 locked into their rocks, dissolved in their oceans, cycling through their atmospheres, and perhaps in some scenarios, in some futures, incorporated into living things. The carbon and oxygen forged in the nuclear burning shells of this star, the iron made in its silicon burning phase, the gold and uranium created in the final seconds of its explosion, all of it scattered across light years of space, waiting for gravity to gather it again into new configurations, new structures, new forms. This is not poetry. It is nuclear astrophysics. The heavy elements in your body trace back to stars that exploded before the sun formed. The iron in your blood, the calcium in your bones, the phosphorus in your DNA, each of these atoms was synthesized in a stellar interior and distributed through the galaxy by an explosion not unlike the one that will end Stevenson, Ard al-Shabar. You are made of stellar debris. Your atoms have histories spanning billions of years. They have been inside stars, inside supernovae, inside the cold interstellar medium, inside a molecular cloud, inside the solar nebula, inside the Earth, inside countless organisms across the history of life, before assembling briefly into the configuration that reads these words. The death of the largest known star is not a remote event with no connection to human existence. It is the next chapter in a story that produced the atoms comprising every living thing on this planet. When Stevenson 2-18 explodes, it will continue the cosmic recycling that has been operating since the first stars lit up 300 million years after the Big Bang. The star will die. The material will scatter. The story will continue. And somewhere in the galaxy 20,000 light-years away, the largest known star may have already written that ending. The light carrying news of its death may be crossing interstellar space at this moment, approaching us at 670 million miles per hour, bringing a message that left its source before the last ice age ended on Earth. We are waiting for it. We may be waiting for a long time. Or the flash may arrive tomorrow. There is a question that follows naturally from everything considered so far. A question that the existence of Stevenson 2-18 makes unavoidable. If a star can grow to 2150 times the radius of our Sun, if the universe permits objects this extreme, what prevents something larger? Why does the record stop here? Why not 3000 solar radii? Why not 5000? Why not a star that swallows not just the inner solar system but the entire solar system out past Neptune and the Kuiper Belt and the distant Oort cloud? The answer reveals something fundamental about the relationship between mass luminosity and the physics of stellar structure. It reveals why the largest stars are not the heaviest stars. It reveals why nature has a preferred mass range for producing extreme dimensions, and why outside that range, the stars that form either never grow large or strip themselves bare before they can. And it reveals that Stevenson 2-18 does not simply hold a record by chance. It holds a record that sits close to a genuine physical boundary, a limit imposed not by the scarcity of massive objects, but by the physics governing how stars evolve. To understand the limit, you have to begin not with the largest stars, but with the heaviest ones, because the heaviest and the largest are not the same thing, and that distinction is the key to everything. The most massive stars known to exist weigh somewhere between 150 and perhaps 300 times the mass of our Sun. Objects like R136 are one located in the Large Magellanic Cloud within a dense young star cluster called R136 carry masses, estimated at around 200 to 300 solar masses, depending on which measurement technique and which evolutionary model is applied. These are the heaviest stellar objects. The universe produces objects so massive that their existence pushes against the theoretical limits imposed by radiation pressure during the star formation process itself. When a molecular cloud collapses to form a star, the growing protostar's increasing luminosity generates radiation pressure that pushes against the infalling material. For low-mass stars like our Sun, this radiation pressure is modest. Gravity wins easily, and the star continues accumulating mass from its surrounding envelope until the envelope is depleted or dispersed by other processes. For progressively more massive forming stars, the radiation pressure grows stronger as luminosity increases. At some point, for the most extreme cases, radiation pressure becomes strong enough to halt the infall of new material entirely. The forming star blows away its own food supply. This feedback process limits initial stellar masses to roughly 150 to 300 solar masses under most conditions. Stars more massive than this cannot form through normal accretion because their own luminosity prevents it. They reach a self-imposed ceiling determined by the physics of how radiation couples to matter in the infalling envelope. Now, here is the crucial point. These maximally massive stars, these 200 and 300 solar mass objects burning with millions of times the sun's luminosity, are not the largest stars in the universe. They are not even close. R13601, one of the most massive stars known, has a radius of roughly 30 to 35 solar radii. It is an enormous object by any ordinary standard, but it is smaller than Stevenson 2-18 by a factor of roughly 60 inches radius. A factor of 2/0 in volume. The heaviest stars are not the largest stars. The largest stars are not the heaviest stars. Why? The answer lies in how stars of different masses evolve during their lifetimes, and particularly in what happens to their outer layers as they age. Stars more massive than roughly 40 solar masses are so luminous during their main sequence lives that their stellar winds driven by radiation pressure coupling to the spectral lines of heavy elements in the stellar atmosphere carry away enormous quantities of mass throughout the star's life. These radiation-driven winds operate far more powerfully in high-mass stars because the luminosity driving them scales steeply with mass. A star of 100 solar masses radiates with roughly 1,000,000 times the sun's luminosity. The radiation pressure available to drive stellar winds is correspondingly enormous. Over the lifetime of a very massive star, these winds can strip away the entire hydrogen envelope, the outer layer of unburned hydrogen that would in a less massive star expand during later evolutionary phases to produce the bloated red, supergiant dimensions. Without a hydrogen envelope, the star cannot become a red supergiant. The outer layers that would have expanded are gone, shed into the interstellar medium over the course of hundreds of thousands of years. What remains after this stripping is called a Wolf-Rayet star, named after the French astronomers Charles Wolf and Georges Rayet, who first catalogued these objects in 1867. Wolf-Rayet stars are stellar cores exposed to space compact objects, showing the products of nuclear burning in their spectra, because the hydrogen envelope that would normally conceal these regions has been removed entirely. They are hot, bright, and ferociously active, driving further mass loss at prodigious rates. But they are compact, typically only a few solar radii across, despite masses that can exceed 20 solar masses. A Wolf-Rayet star with 25 solar masses has a radius of perhaps 5 solar radii. Stevenson 2-18, with perhaps 20 solar masses, has a radius of 2,150 solar radii. The difference is entirely accounted for by the presence or absence of the hydrogen envelope. Same mass range, radically different dimensions. The envelope is everything. This is why the optimal mass range for producing the largest stellar dimensions falls between roughly 8 and 40 solar masses, a sweet spot where stars are massive enough to evolve into red supergiants with extended convective envelopes, but not so massive that radiation-driven winds strip those envelopes away before maximum expansion can occur. Below 8 solar masses, stars follow entirely different evolutionary paths. They become asymptotic giant branch stars in their late lives, expanding to perhaps a few hundred solar radii before shedding their envelopes as planetary nebulae and leaving behind white dwarf remnants. Hundreds of solar radii sounds large, and by terrestrial standards it is enormous, but it is a factor of 10 or more smaller than the red supergiant dimensions achieved by more massive stars. The physics of the asymptotic giant branch simply does not produce objects in the Stevenson 2-18 size range. Above roughly 40 solar masses, radiation-driven mass loss strips the hydrogen envelope before the star can expand to maximum red supergiant dimensions, producing the compact Wolf-Rayet stars that never achieve extreme radii. Despite their substantial masses, between 8 and 40 solar masses, roughly with the optimal range probably centered somewhere around 20 to 30, solar masses stars retain their hydrogen envelopes long enough to expand fully during the red supergiant phase, reaching the maximum dimensions that stellar physics permits before. The remaining envelope is either shed through stellar winds or the core collapses. Stevenson 2-18, with its estimated initial mass of 25 to 40 solar masses, sits right in this optimal window, not too light to fail to expand significantly, not too heavy to be stripped before maximum expansion. The right mass combined with the right evolutionary timing combined with the right mass loss history producing the extreme dimensions we measure. The theoretical maximum radius for a red supergiant falls somewhere around 2500 to 30000 solar radii, according to the most sophisticated stellar evolution models. This limit is not arbitrary. It reflects the point at which the remaining envelope mass becomes too small to sustain further expansion against stellar wind mass loss and gravitational binding. Stars approach this limit from below during their red supergiant phase, reaching progressively larger radii as mass loss gradually erodes the envelope until the envelope becomes too thin to maintain the extended structure, and the star either collapses or transitions to a different evolutionary state. Stevenson 2-18 at approximately 2150 solar radii sits at roughly 70 to 85% of the theoretical maximum, close to the limit but not at it. This placement suggests that the record could theoretically be broken, that a star at the right evolutionary stage, with the right initial mass and mass loss history, might reach dimensions somewhat exceeding the current record holder. The search for such a star has been conducted to the extent that current technology permits and has not yet succeeded in displacing Stevenson 2-18. The competitors deserve examination both because they reveal the diversity of extreme red supergiants and because the history of the size record reflects the development of measurement techniques over recent decades. VY Canis Majoris held the record for most of the early 2000s. Located approximately 3900 light-years from Earth in the constellation Canis Major, it is one of the most studied and most discussed extreme red supergiants, appearing in countless documentaries and educational materials as the reference example of stellar enormity. Its proximity relative to Stevenson 2-18 allows more detailed observations. Its circumstellar structures, created by decades and centuries of intense mass loss, have been imaged in remarkable detail by the Hubble Space Telescope and ground-based adaptive optics systems. Arcs, knots and filaments of ejected gas surround it at various distances, preserving the record of its recent evolutionary history in spatial form. But size estimates for VY Canis Majoris have proven contentious, with different measurement approaches yielding different results. Early estimates placed it at perhaps 2000 solar radii. Subsequent analyses revised this downward. The most recent comprehensive studies place its radius in the range of 1400 to 1500 solar radii. Still enormous, still placing it among the largest known stars, but clearly smaller than the central estimates for Stevenson. Ard al-Shabaab. VY Canis Majoris lost its record not because it shrank, but because measurement techniques improved and earlier estimates proved over-optimistic. UY-Scuti attracted significant attention in the early 2010s when measurements suggested dimensions potentially rivaling or exceeding Stevenson 2-18, located approximately 5700 light-years away in the constellation Scutum. Interestingly, the same constellation that houses Stevenson 2 UY-Scuti is a pulsating red supergiant that varies in brightness and size over a period of roughly 740 days. Early size estimates ranged as high as 1700 to 1900 solar radii, placing it in direct competition with Stevenson 2-18 for the record. Then Gaia measured its distance more precisely, and the number changed. When the distance to UY-Scuti was revised downward by Gaia's parallax measurements, placing it somewhat closer than previously thought, the physical radius calculated from the same angular size measurement decreased accordingly. Current estimates place UY-Scuti at approximately 1700 solar radii. Still an extraordinary object, but sitting clearly below Stevenson 2-18 inches the size ranking. The record shifted not because the star changed, but because our knowledge of how far away it sits became more accurate. This revision illustrates a fundamental truth about extreme stellar measurements. The numbers are only as reliable as the distances they depend on. Every size measurement for a distant star involves the distance as a multiplying factor. An error of 20% in distance produces an error of 20% in the calculated physical radius. Errors of this magnitude are not unusual for stars in obscured regions of the galaxy, where dust complicates both the distance measurement itself and the correction for extinction that must be applied to brightness measurements. Gaia has reduced these uncertainties dramatically but not eliminated them. For Stevenson 2 to 18, the parallax measurement carries uncertainties reflecting the difficulty of measuring micro-arcsecond shifts for a faint infrared source in a crowded, dusty field. Different analyses of the same Gaia data, using different approaches to handling systematics and uncertainties, produce distance estimates, spanning a range that translates to radius estimates between perhaps 1800 and 2400 solar radii. The central estimate remains approximately 2150 solar radii. The uncertainty is real, but across the full range of reasonable distance and atmospheric model assumptions, Stevenson 2 to 18 consistently places at or near the top of any size ranking. No other star, when subjected to the same careful analysis with the same quality data, produces estimates that consistently exceed it. The question of whether the current record will stand depends partly on physics and partly on how thoroughly we have surveyed the relevant stellar populations. The Milky Way contains on the order of 5 million red supergiants at any given time, based on estimates of the total number of massive stars and the fraction of their lives spent in the red supergiant phase. Detailed size measurements have been made for perhaps a few thousand of these, far less than 1% of the total population. The vast majority remain uncharacterized either because they are too distant for precise measurements or because they are buried behind dust that prevents detection even in near-infrared wavelengths, or simply because they have not yet been targeted for detailed follow-up study. Statistical arguments suggest that the true size distribution of red supergiants extends to some maximum value. If that maximum falls around the theoretical limit of 2500 to 3000 solar radii, then larger stars than Stevenson 2 to 18 might well exist in the unexplored regions of the galaxy waiting for instruments capable of measuring them. If the theoretical limit is more conservative, or if the conditions producing maximum size red supergiants are rare enough that the galaxy contains only one or two at any given time, then Stevenson 2 to 18 might represent a genuine statistical outlier, not just the largest known star, but very close to the largest star that currently exists. The facilities coming online in the current decade will begin to resolve this question. The extremely large telescope under construction in the Atacama Desert of Chile, and expected to achieve first light in the late 2020s, will feature a primary mirror 39 meters in diameter. This is not a modest improvement over existing technology. It is a fundamental change in what is achievable. A 39-meter mirror collects roughly 6 times more light than the largest single mirror telescopes currently operating, and the adaptive optics systems it will employ using deformable mirrors that adjust their shape hundreds of times per second to correct for atmospheric distortion will achieve angular resolutions approaching the theoretical limit imposed by the telescope's aperture. Combined with infrared instrumentation capable of seeing through dust clouds thicker than those obscuring Stevenson 2 to 18, the extremely large telescope will survey stellar populations in the inner galaxy with a clarity that no existing instrument can approach. Red supergiants that are currently detectable but not characterizable will become objects amenable to detailed measurement. Clusters analogous to Stevenson 2, but in more distant or more obscured regions, will become accessible for the first time. The giant Magellan telescope, also under construction in Chile, will combine 7 individual 4-meter mirrors into an effective aperture of 25 meters, providing complementary capabilities for high-resolution infrared spectroscopy. The 30-meter telescope planned for Hawaii, pending ongoing discussions about its site, would provide similar capabilities in the Northern Hemisphere. The James Webb Space Telescope, operating since 2022, has already demonstrated extraordinary infrared sensitivity that extends systematic surveys of obscured galactic regions to depths impossible from the ground. Webb cannot achieve the angular resolution of the large ground-based facilities in their final configurations, but its freedom from atmospheric absorption at mid-infrared wavelengths allows it to detect stellar populations invisible even to ground-based infrared observatories. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will survey large areas of the sky at near-infrared wavelengths, with sensitivity approaching Webb's, but covering areas of sky hundreds of times larger. Roman's wide-field capability makes it ideal for discovering rare objects that might hide anywhere within accessible survey volumes. Objects like extreme red supergiants that appear at random positions across the galaxy rather than concentrating in any predictable location. These facilities will conduct the most comprehensive census of extreme stellar objects ever attempted. Within the next decade or two, the question of whether larger stars than Stevenson 2 to 18 exist in the Milky Way will move from unanswerable to answerable, at least for the portions of the galaxy accessible to these instruments. The record may fall. If it does, the new record holder will almost certainly be a red supergiant in the same mass range as Stevenson 2 to 18, located in a similarly obscured region of the inner galaxy, discovered through the same infrared techniques that revealed the current champion. The physics constraining the maximum stellar size does not change. The size of the unexplored stellar population does. If the record stands, if no larger star is found, despite comprehensive surveys of the regions where such objects should preferentially exist, that result will itself be scientifically significant. It will constrain the upper tail of the red supergiant size distribution in ways that can be compared with theoretical predictions, testing whether our models of stellar structure and mass loss correctly capture the physics that limits how large a star can grow. Either outcome advances understanding. Either outcome tells us something real about the universe. This is the nature of science practiced at the boundary of knowledge, the boundary where every measurement either breaks a record or confirms that the record reflects a genuine physical limit. For now, Stevenson 2 to 18 holds its position, confirmed by multiple independent measurements, consistent with theoretical limits, located in a star cluster that seems almost designed to produce extreme objects at the right distance, to be measurable with current technology at the right evolutionary stage to display its maximum dimensions. The largest known star in the observable universe. Known. That qualifier matters. The word carries a weight that honest scientists do not dismiss. What we know is bounded by what we have looked at, and we have looked at a small fraction of the available sky, with sufficient precision to characterize stellar dimensions at this level of detail. Beyond the boundary of current knowledge, in the dust-shrouded inner regions of the galaxy, in the crowded star-forming regions where massive stars preferentially form in the clusters and associations we have not yet surveyed with adequate infrared sensitivity, the universe may be keeping larger secrets. We have not yet seen everything. We have not yet measured everything. The survey continues. Return for a moment to the beginning. You are standing outside on a clear night. The air is still. Above you, the sky is dark enough that the Milky Way is visible, that faint smear of light stretching from horizon to horizon, the combined glow of hundreds of billions of stars, too distant to resolve individually but too numerous to disappear entirely into the background darkness. You have stood under a sky like this before, perhaps many times. Perhaps you have felt in those moments something that resists easy description, a sensation combining smallness and wonder in proportions that shift depending on the night and your mood and what you carried into the darkness with you. Now you know something you did not know before. Somewhere in that smear of light, in a direction that looks toward the inner spiral arms, in a region of sky that gazes toward the densest and most obscured parts of the Milky Way, there is a star burning right now that could swallow everything between you and the outer solar system without noticing. A star that outshines nearly 500,000 suns. A star whose surface would sit, if placed at the center of this solar system, just beyond the rings of Saturn. A star so vast that the airplane you might board tomorrow flying at cruising speed would need 400,000 years to cross its diameter. You cannot see it. The dust is too thick. The light it emits in visible wavelengths never reaches your eyes. It has been burning for 20 million years and will likely burn for some time yet. And in all of human history, from the first person to look up at this same sky to the scientists who measured this star's dimensions using infrared telescopes and space-based parallax instruments, no human being has ever seen it with unaided eyes. It was always there. We simply had not yet learned how to look. There is a specific kind of knowledge that changes not what you do but what you are aware of carrying with you. Learning that the universe is 13.8 billion years old does not change your morning. Learning that light takes 8 minutes to reach us from the sun does not alter your afternoon. Learning that Stevenson 2-18 exists, that it is real, that it has been measured and confirmed and placed within our understanding of stellar physics. None of this changes the practical texture of daily existence in any way that matters for most purposes. And yet something shifts. The sky you look at after encountering this knowledge is not the sky you looked at before. Not because the sky changed, because you changed, because your awareness of what the sky contains has expanded to include an object that permanently alters the scale against which everything else is measured. The stars you can see with your eyes, which already seemed impossibly remote and impossibly vast by any terrestrial standard, are now contextualized against a background that contains something larger still. The sun that warms you already incomprehensibly large by human standards is now a basketball beside a sphere taller than any building on Earth. This is what astronomical knowledge does when it works the way it is supposed to work. It does not make the world smaller, it makes it larger. It extends the territory of the comprehensible outward into regions where intuition fails and measurement must substitute until the map of what is known begins to approach, however inadequately, the scale of what actually exists. We have been extending this map for 4 centuries since Galileo first turned a telescope toward Jupiter and discovered moons that nobody knew were there. Each generation of astronomers pushed the boundary of the known outward. Each new instrument revealed phenomena invisible to all previous instruments. The progression has not been smooth or linear. It has been punctuated by revolutions, by moments when a new technology or a new theoretical framework transformed not just what was known, but what could be asked. The discovery of infrared astronomy was such a revolution. It did not merely extend existing surveys to new objects. It revealed that an entire population of the universe, stars, galaxies, stellar clusters, the most obscured and extreme objects in the Milky Way, had been completely invisible to all prior astronomical work. The universe was not just larger than previously mapped. It contained things that the mapping methodology itself had been constitutionally incapable of detecting. Stevenson 2-18 is one product of this revolution, a star that could not have been discovered by any instrument or technique available before. Roughly the 1980s characterized with any precision only in the 2010s, with the help of space-based astrometry that did not exist a decade earlier. A record holder that was until very recently not merely unknown but unknowable. The atoms in your body have a history that makes this star feel personal in a way that purely numerical scale comparisons cannot capture. Every carbon atom in your body was synthesized in the core of a star that completed its life before our solar system formed. The triple alpha process, the sequence of reactions by which 3 helium nuclei combine to form carbon, 1-2 created that carbon, in conditions not unlike those operating in the helium-burning shell of Stevenson 2-18 right now. Every oxygen atom you have ever inhaled was forged in the same way. Every calcium atom in your skeleton, every phosphorus atom in the molecular machinery of your cells. These atoms did not form in the solar nebula that produced the Sun and Earth. The solar nebula was mostly hydrogen and helium, with only trace quantities of heavier elements. Trace quantities that came from somewhere else entirely. They came from stars that lived and died before the Sun existed. Stars that synthesized these elements through the same nuclear processes occurring in Stevenson 2-18 at this moment, and then scattered them through the galaxy in supernova explosions, where they drifted for millions of years through the interstellar medium before being swept up into the collapsing cloud that would eventually become this solar system. You are in a precise and literal sense made of stellar debris, not metaphorically, not as a poetic flourish. The atoms comprising your body pass through at least one and probably multiple generations of stars before arriving at their current configuration. They were inside nuclear burning regions where temperatures exceeded hundreds of millions of degrees. They were ejected in supernova explosions and traveled through interstellar space for millions of years. They were incorporated into the Sun's planetary disk and eventually into the rocky body of Earth. They cycled through geological processes, through ocean chemistry, through the slow development of biological molecules over billions of years, until they assembled into the particular arrangement of atoms that constitutes a living human being capable of reading about the largest star in the observable universe. The iron in your blood is not merely similar to the iron that accumulates in the core of Stevenson 2-18 and will eventually trigger its collapse. It is the same element forged by the same nuclear process, distributed by the same kind of explosion, participating in the same cosmic recycling that has been operating since the first generation of massive stars exhausted their fuel and detonated 300 million years after the Big Bang. You are connected to Stevenson 2-18, not by proximity or interaction, but by origin, by the shared fact that both you and it are products of the same universe, operating the same physical laws over the same 13.8 billion years of cosmic history. That connection is as real as any connection can be. Consider what it required to discover this star. It required the development of semiconductor physics in the 20th century to produce the infrared detectors that can see through galactic dust. It required the development of cryogenic engineering to cool those detectors to temperatures approaching absolute zero, suppressing thermal noise enough to detect faint astronomical signals. It required the development of space launch capability to place telescopes above Earth's atmosphere, where infrared wavelengths blocked by atmospheric water vapor could finally be observed. It required the development of digital computing powerful enough to process the data streams from these instruments and compare billions of measured stellar positions with theoretical predictions. It required the development of stellar atmosphere models refined over decades of careful theoretical and observational work. It required the Gaia mission's 17 years from conception to the data releases that enabled precise parallax measurements for this star, representing an investment of thousands of person-years of engineering and scientific effort. And before all of that, it required the accumulated scientific inheritance of 4 centuries of astronomical practice. Newton's laws of gravity and motion, the discovery that stars are other suns at vast distances, the development of spectroscopy that allowed stellar temperatures and compositions to be measured remotely, the understanding of nuclear physics that explained how stars generate energy, the stellar evolution models that predict what a star should look like at each stage of its life. Every person who contributed to any of these foundations contributed without knowing it to the eventual discovery and characterization of Stevenson 2-18. The knowledge is collective. The achievement belongs to no single moment or individual, but to the entire enterprise of science practiced across generations, each generation standing on what the previous one built, each advance making the next advance possible. This is what human civilization has been doing among all its other activities for 400 years of systematic astronomical observation, building incrementally and collectively a map of what exists, pushing the boundary of the known outward against the vast darkness of the unknown. Not because there is any immediate practical benefit, the existence of Stevenson 2-18 has no effect on terrestrial concerns, on the immediate problems of the world, on the daily lives of the vast majority of the human beings alive today. But because knowing is valuable, because understanding the universe we inhabit is part of what it means to be the kind of beings we are, because the capacity to ask what is out there and to develop the means to answer that question is one of the distinguishing characteristics of the species that built those instruments and trained those astronomers and funded those missions. We are the only known matter in the universe that wonders about the universe. That remains true whether or not it implies significance in some larger cosmic sense. Whatever the universe thinks of human curiosity, and the universe, as far as we can tell, thinks nothing at all, the curiosity itself is extraordinary. Atoms that formed in stellar cores, scattered by supernova explosions, assembled over billions of years into configurations capable of examining the very processes that made them, matter that can measure its own origins. That is what happened when astronomers pointed infrared telescopes at a dense cluster in the direction of Scutum and found buried beneath 20 magnitudes of dust extinction a star so large that it could swallow the inner solar system. Matter measured matter. The universe became aware of one more detail of itself. The light that left Stevenson 2-18 and reached the infrared detectors that characterize its size today departed the star approximately 20,000 years ago. At that moment, human beings were painting animals on cave walls in what would eventually be called Europe. They were crossing land bridges and coastlines populating continents that no human had yet walked. They had no written language, they had no mathematics, they had no concept of stars as distant suns, no framework for understanding the nature of the light they saw in the night sky, no capacity to imagine the scale of what they were embedded in. The photons from Stevenson 2-18 traveled toward them anyway. Those particular photons at visible wavelengths were absorbed by dust thousands of light years short of Earth and never arrived. But the photons at infrared wavelengths, the ones that would eventually be captured by instruments not yet built by technologies, not yet conceived by a civilization, not yet imagined, continued their journey through 20,000 light years of interstellar space. They are still arriving. The instruments are recording them now as you read this. Each infrared photon that reaches a detector carries information about the state of the stellar atmosphere as it existed 20,000 years ago, when everything that would eventually become human civilization was still gathering around, fires and wondering about the lights overhead. Somewhere in the opposite direction, radiating outward from Stevenson 2-18 toward the rest of the galaxy, other photons are currently traveling that were emitted today at whatever moment constitutes the star's present. Those photons will reach Earth in 20,000 years. Whatever exists here to receive them will be as remote from us as we are from the cave painters who unknowingly shared the sky with this star's ancient light. Whether this star still burns in its present moment, whether the iron core has crossed its threshold, whether the collapse has already occurred, whether the light from that explosion is already crossing interstellar space toward us, we cannot. I know. The finite speed of light preserves these uncertainties with mathematical certainty. There is no way to ask the question and receive an immediate answer. The universe does not permit simultaneous knowledge of distant events. We wait in the only way available to us. We keep the detectors running. We monitor the neutrino observatories. We watch the infrared sky for brightening. We build better instruments that might catch the early signs of instability that theory suggests should precede the final collapse. And we continue doing what astronomers have always done, observing, measuring, comparing, refining, pushing the boundary of the known one careful step at a time. 20,000 light-years away, in a direction the naked eye perceives as darkness, the largest known star in the observable universe burns. Its surface extends across a volume that could contain 10 billion copies of our Sun. Its light too dim in visible wavelengths to reach our eyes through the intervening dust blazes in the infrared with the combined power of nearly 500,000 stars. Its outer atmosphere is thinner than any vacuum we can produce in a laboratory, yet it glows with the ruddy color of a coal at the edge of burning. Deep within it, in a region smaller than Earth, at the center of an object larger than Saturn's orbit, iron accumulates in a core that has been building toward a threshold since the silicon burning phase began. The star does not know this. Stars know nothing. They are not conscious. They do not experience their own existence or contemplate their approaching ends. They are nuclear furnaces held in shape by the balance between gravity and radiation burning through successive fuels, according to the equations of physics, evolving along paths determined entirely by their initial mass and the laws of the universe. The knowing falls to us. We are the part of this story that knows it is a story. We are the matter that became aware of matter. We are the atoms that learned to ask what they are made of, and found in the asking that they were made of the debris of stellar explosions, that the same processes occurring in Stevenson 2-18 at this moment have been occurring in stars throughout the galaxy for billions of years, building the elements of which, all complex chemistry, all rocky planets, all liquid water, all biology, all thought is made. The largest known star and the smallest conscious observers are part of the same universe, subject to the same laws, participating in the same ongoing story of matter organizing itself into increasingly complex and eventually self-aware configurations over billions of years of cosmic time. We found it, we measured it, we placed it within our understanding of how stars live and die. We traced its origin to a collapsing molecular cloud 20 million years ago, its evolution through successive burning phases to its current bloated red state, its eventual fate to a core collapse that will produce either a city-sized ball of neutrons or a gravitational abyss from which nothing escapes. We did all of this without leaving this planet, without approaching within 20,000 light-years of the object, using instruments built from materials forged in stars that died before the sun was born, operated by minds assembled from atoms with billion-year histories, informed by knowledge accumulated across 4 centuries of careful observation and theoretical refinement. That achievement, modest against the scale of what it describes, extraordinary against the scale of what produced it, is the real wonder this star reveals. Not that the universe contains something so large, that the universe contains something small enough and brief enough and improbable enough to notice. Tonight, somewhere above you, ancient light is still arriving. Photons that left Stevenson 2 to 20,000 years ago, carrying information about the outermost layers of the largest known star, are reaching Earth at this moment. Most will pass through without interacting with anything. A handful will strike the mirrors of infrared telescopes and register on detectors cooled to temperatures approaching absolute zero. The measurements will be recorded. The data will be analyzed. The knowledge will accumulate one photon at a time, one careful measurement at a time, one generation of astronomers building on the previous, pushing the boundary of what is known a little further into the vast dark. The star burns. We are watching. And the light keeps coming,